welcome to this problem walkthrough. Today, we're exploring an interesting problem titled Widest Vertical Area between two points containing no points. We'll dive into the problem statement, discuss some potential approaches, and analyze the solution in detail. Let's get started. In this problem, we are given an array called points, where each element represents a point on a 2D plane in the form x_i, y_i. Our task is to determine the widest vertical area between 2 points such that no other points from the input array lie inside this area. The key here is that points lying exactly on the boundaries of the vertical area are allowed, but no points should exist strictly within the area. Ultimately, we need to return an integer representing the maximum width of such a vertical area. A vertical area is defined by the space between two vertical lines, and its width is simply the absolute difference between the x-coordinates of the two lines. Let's look at an example to clarify. Suppose the input array of points is 87, 99, 74, 97. The x-coordinates of these points are 8, 9, 7, 9. By sorting these x-coordinates, we get 7, 8, 9, 9. Now, we calculate the gaps between consecutive x-coordinates, 8, 7 equals 1, 9, 8 equals 1, and 9, 9 equals 0. The widest gap here is 1, which means the width of the widest vertical area is 1. So, the output for this example is 1. Now, consider another example where the input array of points is 31, 90, 10, 82, 76. The x-coordinates of these points are 3, 9, 1, 8, 7. After sorting, we get 1, 3, 7, 8, 9. The gaps between consecutive x-coordinates are calculated as follows: 3, 1 equals 2, 7, 3 equals 4, 8, 7 equals 1, and 9, 8 equals 1. Among these, the widest gap is 4, so the output for this example is 4. This demonstrates how sorting the x-coordinates helps us quickly identify the largest vertical area. To solve this problem, we must also consider the constraints and edge cases. The constraints specify that the number of points, n, ranges from 2 to 100,000, and each point has x and y values between 0 and 1 billion. This means our solution must handle large inputs efficiently. Sorting the x-coordinates has a time complexity of n log n, which is optimal for this input size. As an edge case, if all the points share the same x-coordinate, the output should be 0, since there are no distinct x-coordinates to form a vertical area. Additionally, if multiple points have the same x-coordinate but different y-coordinates, we only consider the x-coordinate once for determining gaps. These considerations ensure our solution is both correct and efficient. To solve this problem, we considered multiple approaches. The first is the brute force method. The intuition here is simple: calculate the vertical distance, which is the difference in x-coordinates, between every possible pair of points. Then, identify the maximum gap where no other points lie in between. In terms of implementation, this means iterating through all unique pairs of points, calculating the absolute difference of their x-coordinates, and keeping track of the largest difference. However, this approach has a significant downside. Its time complexity is n squared, as we need to compare every pair of points, and its space complexity is 1, since no extra data structures are used. While conceptually straightforward, the quadratic time complexity makes it highly inefficient for larger inputs, where the number of points, n, is large. So, we needed a more efficient solution. This leads us to the optimized sorting approach. Here, the key idea is that the widest vertical gap can be found by focusing solely on the x-coordinates. By sorting these x values, the largest gap will exist between two consecutive x-coordinates in the sorted list. The process involves extracting the x-coordinates, sorting them, and computing the difference between each consecutive pair to find the maximum gap. This approach is much faster, with a time complexity of n log n, dominated by the sorting step. It's a significant improvement over the brute force method. The optimized sorting approach also has a space complexity of n, accounting for the additional space used during sorting. Its advantages are clear: it's significantly faster than the brute force approach and avoids unnecessary comparisons by focusing only on the x-coordinates. By leveraging sorting, it efficiently identifies the widest vertical area without requiring additional assumptions. An alternative approach we considered is the bucket-based method. The intuition here is to use bucket sorting for the x coordinates, dividing the range of x values into buckets. The widest gap can then be found by analyzing the gaps between non-empty buckets. This method is promising in theory, as it can achieve an ideal time complexity of O(n), depending on the bucket size and distribution of the x coordinates. However, its implementation is more complex. It requires pre-processing the range of x values and determining bucket sizes dynamically. Additionally, its real-world performance is highly dependent on the data distribution, which makes it less reliable. While the bucket-based approach is theoretically faster in certain cases, its complexity and dependency on data characteristics make it less appealing compared to sorting. After evaluating these methods, we chose the optimized sorting approach as the best balance between simplicity, efficiency, and reliability. Sorting the x coordinates ensures a consistent runtime of O(n) log n, which is well suited for the given input size constraints. Unlike the brute force method, it avoids unnecessary pairwise comparisons, and compared to the bucket-based approach, it's easier to implement and doesn't rely on assumptions about the distribution of the data or bucket sizes. There were a few key observations that guided us to this realization. First, the problem is fundamentally about identifying gaps between x coordinates rather than y coordinates, which simplifies the scope considerably. Sorting the x values directly aligns with the goal of finding the largest consecutive gap, as the widest vertical area can only exist between two adjacent x values in the sorted list. This clarity was the aha moment that eliminated the need for more complex solutions like pairwise comparisons or bucket preprocessing, allowing us to focus on a more streamlined and deterministic approach. When comparing these strategies, each has its trade-offs. The brute force approach, while useful as a conceptual starting point, is far too slow for large inputs due to its O(n)² time complexity. The bucket-based method, while theoretically faster in some cases, introduces additional complexity and relies heavily on the distribution of the x coordinates, making it less predictable. On the other hand, the sorting approach stands out as efficient, easy to implement, and robust for all valid inputs. Its deterministic time complexity, combined with its simplicity, makes it well suited to this problem. There are no additional assumptions or pre-processing requirements, which adds to its reliability. Ultimately, these factors make the sorting-based solution the clear choice for solving this problem effectively and efficiently. To solve this problem, we aim to determine the maximum vertical distance between 2 points based on their x coordinates, ensuring no other points exist between them. The brute force approach involves iterating over all unique pairs of points, so let's break it down step by step. First, we define the input, which is a list of points where each point is represented as a tuple, x, y. The x-coordinate determines the horizontal position, while the y-coordinate represents the vertical position. For example, the input could look like 3, 2, 7, 5, 1, 4, 9, 1. Next, to evaluate all possible pairs, we use two nested loops. The outer loop picks the first point, and the inner loop picks the second, resulting in a total of n*(n1/2 unique pairs for n points. For each pair, we calculate the absolute difference in their x coordinates using the formula abs, x2, x1. This gives us the vertical distance between the 2 points, which we will use for further checks. After calculating the absolute difference in x coordinates for a pair of points, the next step is to validate this gap. Specifically, we need to ensure that no other points in the input have x coordinates that lie strictly between x1 and x2. This check guarantees that the calculated distance represents a valid vertical area as per the problem constraints. If no intermediate points are found, we compare the calculated distance to our current maximum distance. If the distance is larger, we update the maximum distance accordingly. After processing all pairs of points, the algorithm finally returns the maximum distance as the result. The brute force approach is straightforward but computationally expensive. It requires O(n)² time to generate all pairs and an additional O(n) for each pair to check for intermediate points, leading to an overall complexity of O(n³). An important observation is that this inefficiency arises because we repeatedly check for intermediate points in an unsorted list. By sorting the points by their x coordinates, we can significantly optimize this process and reduce the complexity. In terms of data structures, the problem uses a simple list of tuples to store the input points. Each tuple contains the x and y coordinates of a point, and this structure allows for efficient iteration and access. We also maintain a single variable to track the maximum distance, updating it whenever a larger gap is encountered. To illustrate the algorithm, consider the input points 3, 2, 7, 5, 1, 4, 9, 1. We start by initializing max_distance to 0. As we iterate through pairs, we calculate the x-coordinate difference and check for intermediate points. For the pair 3, 2, and 7, 5, the distance is 4, but point 1, 4 lies between them, so we skip this pair. 4, 3, 2, and 9, 1, the distance is 6, and no points lie between, so we update max_distance to 6. This process continues for all pairs, and in this example, the output is max_distance equals 6. Finally, let's address some edge cases and potential optimizations. If the input contains only one point, the maximum distance is 0, since there are no pairs to compare. For collinear points, such as those aligned vertically or horizontally, the algorithm remains unaffected but may require additional clarification in the problem constraints. Duplicate points, where 2 points share the same x-coordinate, contribute 0 to the maximum distance since the gap is non-existent. To optimize the brute force approach, sorting the points by their x-coordinates is highly effective. Once sorted, the problem reduces to analyzing consecutive gaps in the x-coordinates, eliminating the need for nested loops and intermediate checks. This optimization drastically improves the time complexity from O(n) cubed to O(n) log n due to the sorting step, making it far more efficient for large inputs. This implementation solves LeetCode problem number 1637 by efficiently determining the widest vertical area between any 2 points. The function maxWidth of vertical area starts by extracting all the x-coordinates from the input list of points using a list comprehension. This ensures that only the x values are considered, as the y-coordinates are irrelevant for vertical areas. Next, the x-coordinates are sorted in ascending order. Sorting is crucial because it allows us to calculate the gaps between consecutive x values directly. The sorting step has a time complexity of O(n) log n, where n is the number of points. After sorting, the algorithm initializes a variable max_width to store the maximum vertical gap encountered so far. It then iterates through the sorted x-coordinates starting from the second element, index 1. For each pair of consecutive x values, it calculates the difference, gap, and updates max_width if the current gap is larger than the previously recorded maximum. Finally, the function returns max_width, which represents the widest vertical area. This solution is efficient, with a time complexity dominated by the sorting step, making it O(n) log n. The space complexity is O(n) due to the storage of x-coordinates. The implementation handles edge cases such as input with a minimal number of points, e.g., 2 points, correctly, as the loop will run exactly once in such scenarios. Overall, the solution is concise, efficient, and leverages the key insight that sorting simplifies the problem of finding the widest gap. This is the Java implementation of LeetCode problem number 1637, widest vertical area between 2 points containing no points. The solution mirrors the Python logic, leveraging Java-specific constructs such as arrays and the arrays.sort method. The program extracts x-coordinates, sorts them, and calculates the maximum gap between consecutive x-coordinates. Java's strong type declarations and array manipulations ensure efficient handling of the input. To start, we're given the input points 1, 1, 3, 3, 7, 5. The first step is to extract the x-coordinates from these points, which gives us 1, 3, 7. Next, we sort these x-coordinates in ascending order, which in this case results in the same list, 1, 3, 7. After that, we initialize a variable called max_width to 0. This variable will keep track of the widest gap between consecutive x-coordinates as we process the list. Finally, we calculate the gaps between each pair of adjacent x-coordinates. The gap between 3 and 1 is 2, so we update max_width to the maximum of 0 and 2, which is 2. Then, the gap between 7 and 3 is 4, so we update max_width again to the maximum of 2 and 4, which gives us 4. After calculating all the gaps, we find that the widest gap is 4. This is the maximum width of a vertical area between 2 points containing no other points. So, the output for this example is 4. Now let's look at a slightly different input, where some points have the same x-coordinate. Here, the points are 5, 2, 5, 5, 10, 1, 15, 3. Extracting the x-coordinates gives us 5, 5, 10, 15. After sorting, the x-coordinates remain 5, 5, 10, 15. As before, we initialize max_width to 0, and we'll calculate the gaps between these sorted x-coordinates. Looking at the sorted x-coordinates 5, 5, 10, 15, we start calculating the gaps. The first gap is between the two 5's, which is 5, 5 equals 0. Since the gap is 0, max_width remains unchanged at 0. Next, the gap between 10 and 5 is 5, so we update max_width to the maximum of 0 and 5, which is 5. Finally, the gap between 15 and 10 is also 5, but since max_width is already 5, there's no change. At the end of these calculations, the maximum width remains 5, so the output for this example is 5. Now, let's consider an input with more points and a wider range of x-coordinates 1, 2, 2, 3, 4, 5, 8, 6, 10, 7. First, we extract the x-coordinates, which gives 1, 2, 4, 8, 10. These x-coordinates are already sorted, so there's no need to reorder them. We initialize max_width to 0 and calculate the gaps between adjacent x-coordinates. The gap between 2 and 1 is 1, so max_width becomes the maximum of 0 and 1, which is 1. The gap between 4 and 2 is 2, so max_width updates to 2. The gap between 8 and 4 is 4, so max_width becomes 4. Finally, the gap between 10 and 8 is 2, but since max_width is already 4, it doesn't change. After completing these calculations, we find that the widest vertical gap between 2 points, containing no other points, is 4. So, the output for this example is 4. By following this approach, extracting x-coordinates, sorting them, and calculating the gaps, we can determine the maximum width efficiently for any given set of points. This concludes the solution walkthrough for this problem. To analyze the time complexity of the solution, we can break it down into 3 main steps. First, we extract the x-coordinates from the input list of points. This involves iterating through all the points once, which takes n time since we process each of the endpoints exactly once. Next, we sort the extracted x-coordinates. Sorting is the most computationally expensive step, requiring n log n time due to the logarithmic factor introduced by the sorting algorithm. Finally, we calculate the widest gap by iterating through the sorted x-coordinates and computing the differences between consecutive elements. This is a single pass over the list, which takes n time. When we combine these steps, the overall time complexity is dominated by the sorting step, giving us a total time complexity of n log n. Now, let's look at the space complexity. First, the input list of points requires n space, as it contains n points, each represented as a pair of x and y coordinates. Then, we create an auxiliary list to store the extracted x-coordinates, which also requires n space since it holds one value for each point. For the sorting operation, Python uses timsort, which is an in-place sorting algorithm. This means that the sorting step does not require additional memory for intermediate computations, contributing only one auxiliary space. Combining these, the total space complexity is determined by the input storage and the auxiliary list for x-coordinates, resulting in n space complexity. Let's compare this optimized approach to a brute force solution. In a naive approach, we would calculate the vertical gap between every pair of points and then find the maximum gap. This requires iterating through all pairs, which results in a time complexity of n squared, due to the nested loops. The space complexity would remain n, as we only need space to store the input points. In contrast, the optimized approach avoids the quadratic time complexity by sorting the x-coordinates first and then finding the maximum gap in a single linear pass. This reduces the time complexity to n log n, which is much more efficient for large inputs. The space complexity remains unchanged at n, making the optimized solution far better in terms of scalability. Finally, let's analyze the best, average, and worst-case scenarios for the optimized solution. Regardless of the input distribution, the time complexity remains n log n. Even if the x-coordinates are already sorted, the sorting step still takes n log n time because the algorithm must verify the order. For average cases with randomly distributed points, the time complexity is still n log n. In the worst case, such as when the input is in reverse order, the sorting algorithm handles the data in the same asymptotic time. To summarize mathematically, extracting x-coordinates contributes n, sorting dominates with n log n, and iterating through the sorted list adds another n. Since n log n grows faster than n for large n, the overall time complexity simplifies to n log n. This solution not only improves significantly over the brute force method but also ensures an efficient space complexity of n. When approaching problems like this, it's important to be aware of common pitfalls that can trip you up. First, not sorting the input when required is a frequent mistake. Many algorithms rely on the input being in a specific order to function correctly, especially when calculating gaps or making comparisons. If you skip this step or assume the input is pre-sorted, your calculations may be completely unreliable. Another common mistake is overlooking edge cases. For example, arrays with very few elements, duplicate points, or extreme values like very large or very small inputs can reveal flaws in your logic. Ignoring these can easily lead to runtime errors or incorrect outputs. Lastly, inefficient iteration, like using nested loops in a brute force approach, is another trap. While this might work for small datasets, it often fails for larger inputs, resulting in time limit exceeded errors. Opting for optimized solutions is key to handling large constraints efficiently. Another common area of error involves incorrect gap calculation. After sorting the input, the gaps should be calculated based on the actual values, not just their indices. Failing to do so can result in wrong maximum gap values, especially if the data is not contiguous. Additionally, ignoring problem constraints can lead to logical issues. For instance, assuming all numbers are positive when negatives are allowed, or overlooking potential integer overflow scenarios, can cause failures in edge cases. Always align your solution to meet the constraints provided in the problem to avoid these issues. Now, from an interview perspective, there are a few strategies that can enhance your problem-solving approach. Recognizing patterns is crucial. For many problems involving intervals or gaps, the solution often reduces to sorting the input and scanning for differences. Identifying this pattern early can save valuable time. Also, while starting with a brute force solution might help clarify your thought process, aim to optimize it. Sorting-based approaches are a common improvement, often reducing time complexity significantly. It's also important to ask clarifying questions during interviews. For example, confirm whether duplicates are allowed, if inputs are guaranteed to be integers, or any constraints on input size. Finally, be ready to discuss trade-offs. Brute force may be simpler to implement but slower, while optimal solutions often involve greater complexity but better efficiency. This balance is key in interviews. There are also related problems that can help you practice and refine your approach. For example, LeetCode 164, maximum gap, involves finding the largest difference between successive elements in a sorted array. LeetCode 128, longest consecutive sequence, focuses on identifying sequences in an unsorted array. Problems like LeetCode 189, rotate array, or LeetCode 217, contains duplicate, emphasize input manipulation and efficient handling of duplicates. In terms of alternative approaches, bucket sort can be a practical option when applicable. By dividing the input range into buckets and computing gaps between them, it can achieve linear time in specific cases. However, it requires careful bucket size selection and additional space. Binary search trees can be another approach, where gaps are calculated during an in-order traversal. While efficient for dynamic datasets, they're generally more complex to implement and slower than sorting for static inputs. Each method has its strengths and trade-offs, so choose based on the problem requirements. Great job making it to the end. To summarize, we solved this problem by leveraging sorting for an efficient solution. Along the way, we learned key insights about 2D spatial relationships and optimization techniques. If you found this helpful, please like and subscribe to stay updated on more coding challenges. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!